Hi, I'm Bojana, and I will tell you a little bit about different approaches to that of the ERP that we heard so much about during this workshop. It's somehow a complementary approach, and it's actually auditory attention decoding, but let's get to that slowly. First, what I would like to do is drive the point home, basically, what we're dealing with here. So we have lab experiments like that. As opposed to what we see in real life. Yeah. So there's a huge difference there. Real life sucks. We have to deal with that somehow. Basically, in lab, we have, well, first let's address the goals. So what do we actually want to do here and why? We heard yesterday why we want to go mobile, to find out more about natural processes in the brain, basically. So to find out more about brain in natural situations. But also, what is very nice, and which Stefan also mentioned yesterday, is that this concept of hearables is actually next big thing. So basically, if we can have a device that can be controlled by the brain, and that it can amplify some signal that is important to us from the environment, let's say auditory signal like speech, that would be really cool, even for normal hearing and hearing impaired participants. Individuals. Okay, so this fully functional BCI is something that we can really use. And there are certain challenges that we have to overcome in order to do that. So you've heard a lot about challenges with mobile EEG, but I will just address two of them right now. One is there is a multitude of overlapping stimuli. So basically, we are bombarded every day, in every moment, with visual and auditory information. And there is no isolated stimuli like in a lab, basically. And the next one is the natural scene is a running scene. So basically, it's continuous scene. We cannot just separate one single moment. Well, we can, but we don't capture the whole reality of the situation, basically. So now I'm going to focus on speech as a stimulus, basically as a running, continuous, complex stimulus. But whatever I'm saying now can actually be applied to any other stimulus that has some oscillations in it, be that visual or auditory. So in real life, when somebody is speaking, we can see clearly that, well, we can't see it, but basically a girl is listening to what the guy is saying, and she has some and we're measuring her brain waves, and the thing is that while she is listening to that speech, she's basically reacting to speech pauses, she's reacting to rhythm, speech rhythm, frequency of the voice, and all of that is reflected in neural oscillations. So basically, what we have is that neural oscillations actually follow the oscillation of speech. This is something that we can use because basically neural or brain waves synchronize more to speech that is interesting to us than the speech that we want to ignore. So we can base our BCI on that. And how far we can actually get with that in real life is what we were really interested in here. So we had an experiment where we played two speech streams to the participant, and in the beginning we were really cautious, like very careful, and we recorded high high-density EEG. Basically, we played 2 stories in German and told our participants, okay, focus on one, ignore the other. And this is, I don't know if this is going to play, but...
Nein, es geht nicht anders. Wir müssen uns trennen. Sie teilten die Tiere, so dass jeder einen Löwen ein.
Yeah, so it's not an easy task, especially after 40 minutes of listening and more that we had for our participants. They get tired later and yeah. They do follow though. So what do we do now with our recorded signals? So we have some setup, we record brain waves, we have 2 speech streams. So we can train some sort of a decoder, basically. We put the attended speech into some algorithm, and we put our concurrently recorded EEG, and a decoder comes out. Later, we can use that decoder to basically decide which of the 2 speech streams participant is listening to. So it's going to decide whether it's speech 1 or speech 2, if we give it both speech streams and EEG. The big question is, what do we use here? So what algorithm? Well, there is actually plenty of algorithms by now out there. So for this part, for training phase, we need a lot of data, and for the testing phase, fortunately, we usually need a very short decision window, which means we can probably do this in real time, in real life, which is kind of important for any true BCI application. So basically, which algorithm to use now? There is always a trade-off between algorithms. So on horizontal axis, you can see parameters that are kind of important for training, and parameters that are important for testing on the vertical axis. So here goes how much data we need to train our algorithm, how much computational resources, and over there, what is the speed of our decision making, basically, and what is the accuracy with that speed. So we have two families of algorithms. One is linear methods, the other one is nonlinear methods. So here you can put anything from linear regression to cross-correlation, CCA, and the other one is usually neural networks so far. The difference is that linear models associate EEG to our stimulus in a linear way, nonlinear, of course, in a nonlinear way. So in the beginning, we decided to use linear method because that is something that has been done before by O'Sullivan in 2014. And basically, we used linear regression to train our decoder. We used the decision window of 1 minute. So that's not really real time, but it's been tried before, so let's start with that. So we have 1 minute decision window with 96 channels, and we have our accuracy, basically, of our algorithm. So how well it can distinguish what is the target speech to what is ignored speech. We can see some variation in participants, but they're all about chance, they're all with pretty high accuracies. Rob said something yesterday that I would like to repeat here. This isn't really about how well the algorithm always works or how good the participants are. It's kind of how they think. So it's not something that you can account for sometimes. We would like to do, of course. So basically, what we wanted to do later, what we did, is we started with 96 channels, and then we decreased our number of channels gradually, taking out one channel that is not informative at a time, or that is least informative, and we came up with this curve. So basically, it tells us that at around 15 channels, we still have quite decent accuracy. So with 15 channels, we can do pretty good decision making here. And that is something that we can use for invisible systems, or transparent mobile systems. We want smaller number of channels. We don't want it to be like cap. Of course, you've heard that before. And what we also got from this analysis is which channels are actually informative. So at 15 channels, for example, mostly informative channels are around temporal area for auditory stimulus. It will be different for visual. Now that we know this, we were wondering, okay, can we actually do this with C-grids? So can we make it completely nice and transparent and working? So we organized or set up another experiment. This time we also had C-grids and in combination with high-density EEG. That is because we wanted to compare our results to the previous study. We had, again, 2 speakers, this time both male speakers, so the task was a little bit harder, like that. Our participants still managed to answer most of the questions about the story correctly, and then we first replicated our first study. So basically we have similar results, around 89% accuracy, 88. And again, decision window 1 minute. We shouldn't forget that. And then we wanted to see what happens with C-grids. So we have 16 C-grid channels. So in order to make this comparable with high-density CAP, we took wide distribution of 16 channels on CAP. So when we compare them, the results, the accuracy for C-grids is, let's say, much lower than accuracy for the CAP. And basically, that could be because C-grids do not capture enough, or not enough, but as much information as the CAP does, or as this wide distribution does. So we were wondering, okay, can we actually bring this to the higher level, like this accuracy? Because we really want to do this with C-grids, we really want to do it with small decision windows. And if you remember from before, I spoke about linear and nonlinear methods. So we decided, okay, we want higher accuracy, so let's go to nonlinear methods. They do need a lot more training data, but yeah, that's something that we just have to deal with. So this is also fresh data. I don't have all the participants analyzed yet, but I took 3 of the, let's say, worst performing participants, and you can still see an increase of like 15 to 20% accuracy even. Well, 15, let's not overdo it. So for linear decoding with decision window 1 minute, we get this, so for each participant. For nonlinear decoding with 10-second window, we get much higher accuracies already. So we get shorter decision window and much higher accuracy at the expense of a lot of training data and a lot of time to train a decoder. So, okay, I will just conclude. So attention decoding is actually a complementary approach to the ERP analysis for the running scene, basically. So you take the entire stimulus, the entire EEG signal, and you relate them to each other. This is very convenient for mobile EEG, I believe. And the best part is that it actually works with transparent EEG systems, so like C-grid, so a very small number of electrodes, and it's still working. However, it may be best to focus to nonlinear attention decoding approaches like neural networks, because for real life we do need high accuracies. We don't want our algorithm to reduce the amplitude of the speech that you actually want to listen to by mistake. So this comes, of course, at the expense of more training data and computational resources, but I believe that's actually worth it. So yeah, I would like to thank basically Stefan's lab, and 3 of these people you already seen in this workshop. And yeah, if you have questions, I'm there.
Thank you, Bojana, for this interesting work. Questions?
Yeah, thank you for this very interesting talk again. I was just wondering, how much is your decoding performance, actually the whole system, dependent on the auditory stimulus? So can you also generalize towards different stimuli, or do you then have to retrain all the model?
So far we have done this for different sort of stimuli. So we have done this for speech in different languages with different speakers, but also for noise, like babble noise and just random noise. The thing is that the algorithm can actually recognize that you're attending to noise if you are attending to it, but it wouldn't really tell you, okay, this is noise. So it wouldn't know what sort of signal you're listening to. Does that answer your question?
Okay, but you can still find out that you are actually paying attention to this kind of signal?
Yes, we can.
Nice.
My question also, I guess, is similar. I didn't understand how do you label the data? So how do you know that participant is attending on one speaker or another speaker during the 1 minute's time window?
So so far it's a controlled experiment. So basically we tell our participants, okay, focus on left speaker or focus on the right speaker. So we know which speaker they're focusing on, or hopefully we do. We do ask them questions later also, so we do check. So in real life, we wouldn't have that information, but you would still be able to train the decoder beforehand and on the data that you do know.
How much training data was there for the nonlinear?
Same amount, actually, so 48 minutes.
Oh, I thought it was less for more for the nonlinear.
So it's the same amount of data, it's just smaller windows that we use.
So use the same data,
Yes.
but then you just analyze it using a linear, and then
It would probably be also a lot better if we had a lot more data,
yeah.
but until we record that.
One last question.
Just, second question. How much do you think actually you are dependent on presenting the stimuli always from the same direction? Because I think you do not move the speakers around. You just present it left and right. Do you think that also has an influence?
It's possible that it does. It's not crucial though, because we have done speech decoding from the of 2 speakers presented from the same direction. So it's really more about the oscillation in speech than the spatial information, although the spatial information is a part of it also. Especially if you're doing decoding with neural networks, then it can really find the spatial component sometimes.
Okay, last question.
Yeah, just a more general one. The decoders are usually made subject specific, I think, right? Like a personalized model. And of course you could generalize it and make it based on other data, which is probably a bit less accurate, but still works. But would there be any gain if we combine all the data sets recorded in this way with AAD and combine it all to maybe get additional information? Like like we heard, more data is better, but I don't know if I give my data to you as well. It's a different layout maybe or not, but would it still? Do you think it could still help in some way? Because
that's quite an interesting question. We did a comparison of one decoder trained on subject-specific data and trained on others, data collected from other subjects, and that I can actually show you here. So if we take a pre-trained decoder, which is actually a decoder trained on other participants, we get something like a constant performance around 80%. However, if we take individualized decoder, depending on how much data we have, like after 5 minutes we have 70% accuracy, and later, after like 25 minutes, the individual decoder actually performs a lot better. This is not the case for neural networks. I can't tell you why, and that was actually a huge issue also that presented itself at the conference in Leuven. But basically that's something that we need to look into. In general, it should be better if we use decoders, like average decoders from other participants also, but that reduces accuracy in neural network decoder.
Okay, let's thank Bojana once again and continue discussion